Scientific notation is a notation that we can express numbers in to make them easier to write down. And this is especially useful for large or small numbers where we have tons of decimal places. So the definition of scientific notation is if you have some number n, you can express it in the form of a times 10 to the lowercase n. And so I'll break down what these mean. A is just the first digits of n. That's of capital N, of the number you're expressing in scientific notation. So if you have 1,000, if n equals 1,000, then A would be 1,000 as well. But A specifically, in most cases, is written in with the first digit as the spot right next to the decimal. So you move your decimal over where A is equal to 1.000. So that's conventional. If you have 120, A would be 1.20, for example. Now, so that's what A is. Now, lowercase n is the number of decimal places you move to do this operation. So with 1,000, you originally have the decimal place at this point, and you move it over 1, 2, 3. So n equals 3 in this case. And the decimal place for 120 is here. You move over 2, so n equals 2. So to write it down, the number, that's lowercase n, is the number of decimal places moved for n to equal A. That's the definition of that. Now, I think the best way to learn this and to solidify it in your mind is to just go through some examples. So let's say that we have a number 10,000. How can we write this in scientific notation? First, we can find the individual numbers A and lowercase n. So A is, we look at the first digit and we have a bunch of zeros after, so then we can write it just simply as 1 by putting the decimal point after the first number. And so originally the decimal place is here, so if we want to find n, we move it over to the new spot, which is 4 decimal places, and we're moving to the left, so n is equal to 4. Writing this out in full, n equals 10,000, which is equivalent to 1 times 10 to the 4. So now let's do an example where we have a smaller number and the first number is not equal to 1. So say 0.034. So we've got zeros here, and we want the first non-zero number to be before the decimal. So A is equal to 3.4. And can you see how I got that there? We don't want these trailing zeros to be the first digits, or A. We don't want that to be an A. We want to express it simply as the non-zero digits in that value. And then we can cover those decimal places with that exponent. So we're moving to the right this time. If we want to find n, we go 1, 2. But since this is a negative value, since we're moving to the right, then it's a negative value, so -2. We're making the number bigger, so then we compensate the exponent by making it smaller. So that means 0.034 is equal to 3.4 times 10 to the -2. So that's an example of using a smaller number and converting it to scientific notation. That is a number smaller than 1. So what if we have a number with lots of digits, say 107.216, just to throw a random number out there. It's still simple. We have no trailing zeros or no leading zeros here, so we can write the whole thing out as we'll find A is equal to 1.07216, which can easily be rounded as well if you want to. A lot of times it's good to round it to say 1.07, or even you could do 1.1, whatever you prefer. Then n, we're moving our decimal place over to the first non-zero number, 1, 2. We're moving it 2 spots, so n equals 2. So we get, if we don't round it, you get that this value equals to 1.07216 times 10 to the power of 2. Or, if you round it, 1.1 times 10 to the 2. Both are valid. So these are just a few examples of scientific notation. And as you can see, it is very useful to write. I mean, if you have, like, if I write up here, 1 billion, right, you don't want to write that out every time, so you can just say 1 times 10 to the power of 9, because you've got a 1, you're moving over 9 decimal places, so you have a 9, and it's just so much nicer to write it in that form. Now, another thing to look at is, what if we want to do arithmetic, or arithmetic, is the right way to say that, of numbers in scientific notation. So that would be like addition, or subtraction, or multiplication, or division. What if you want to do that? Well, I will show you some examples of that. Addition, we'll start with. Say you want to add 5 times 10 to the 3 plus 3 times 10 to the 3, which in non-scientific notation is just 5,000 plus 3,000, which we know to be 8,000. But let's do this in scientific notation form. So for addition, what we do is we can first add these values together, the A values of each number. So we know that equals 8. Now we've got these exponents, and since these exponents are the same, we can just tack it on the end, because it's the same exponent number, so you just need to add these values. So now I'll do an example where we don't have the same exponent values. So if you have 3.2 times 10 to the 2 plus 4.3 times 10 to the 4. So it's 320 plus 43,000. How do we do this? Well, like before, well, not like before actually, because we have these values, we can't just add these two together, and we can't add these two together because they have different exponents. So what we do is we want to express this in the same form. That is, have either both of these equal 10 to the 2 or both of them equal 10 to the 4. And so what we're going to do is we're going to make this value expressed as 10 to the power of 4. How we do that is we move the exponent over, and then we can compensate for that in the exponent. So in this case, we can move this exponent over 2 points, 0.032 times 10 to the 4, which is equivalent, if you move it back, you would subtract 2, right, like we did before on the last page, and that would give you 3.2 times 10 to the 2 again. So they're equivalent numbers. Now we've got the same number here, 3.4 times 10 to the 4, and now we have the same exponents, and so that means we can simply just add the A values. So that means we get 4.332 times 10 to the 4. And so that's how you tackle those additions. You want to have them where you have the same exponents with base 10, and then you can simply just add the a values together. For subtraction, it's exactly the same, except you subtract these two numbers. Now, moving on to multiplication. This one is a little bit different. So say you take 3 times 10 to the 2, or 300 in regular notation, and multiply it by 6 times 10 to the 3, or 6,000. So I'll put brackets around it just to differentiate the two scientific notation numbers. Now what you do in this case is similar to addition, is you can multiply the first numbers of each. So 3 times 6 is 18, and then we have our times 10 to the exponent. Now this case, we're multiplying these exponents together, and if you remember exponent laws from math class, when you multiply exponents with the same base, like when you multiply with the same base, you can add the two exponents. So this would be 10 to the 2 plus 3 power, otherwise known as 5. 18 times 10 to the 5. Now, if you notice, I've written this out as 18, which the decimal place is here, and like I mentioned, we normally want it here. Now this is okay to have it this way. It's not really conventional, and it's much nicer to write it with the decimal point back before or behind the first number. So what you can do is kind of similar to what we did up here, where we changed this power of 2 to power of 4, is we move this back 1 and then increase the exponent. So instead of 18 times 10 to the 5, you get 1.8 times 10 to the 6, which is also known as 1 million, or 1.8 million. And so that's how you do that. Now division is a lot the same. Say you have 8 times 10 to the 6, or 8 million, and divide by 2 times 10 to the 4. So 8 million divided by 20,000. What you do is you take the a values and you divide them. So 8 divided by 2 is 4. Then, using exponent laws again, if you have a division of exponents that have the same base, you subtract the exponents. So you subtract the exponent from the numerator with the exponent in the denominator. So 6 minus 4, which you get 4 times 10 to the 2, or 400. And so this has been working with scientific notation and learning how to do arithmetic with it. And this is something that's very useful, that will come up a lot, and it especially, like I mentioned, with very large or small numbers. So it's good to become familiar with, good to practice, and it's definitely important for physics. So definitely make sure that you work on that.